We are looking at a paper today called LongHorizon-Harness. It's Advancing Long Horizon Agents for Real-World Tasks by Ziyu Ma and the DreamX team at Alibaba Group.
And honestly, if you are an ML engineer or, a researcher building AI agents, you really need to hear this one.
Yeah, absolutely, because it fundamentally redefines why your agents are failing at complex tasks. The core insight here is that current agent harnesses fail at long horizon tasks because they basically cram execution, state tracking, and self-assessment into a single, ever-growing context window.
Right, which just leads to massive compounding errors and, context rot.
Exactly. And this paper fixes that via a Manage-Execute-Audit, or MEA loop. By externalizing the task state and forcing a memory-wiped executor to be independently verified by read-only auditor before a manager updates the state, the system gets these massive performance gains without even changing the underlying model.
The numbers are wild. Pass rates jump from 51.8% to 80.7% on WeaveBench.
And OSWorld 2.0 completion rates literally triple. It basically proves that agent capability is a system-level property, not just a model-level one. So yeah, welcome to AI Paper Slop, the YouTube series where we do a deep dive into the research you actually need to know.
The big shift here, I think, is moving away from the assumption that if an agent fails, we just need a larger parameter count.
Right. Just throw more compute at it.
Exactly. We have been so focused on making the models themselves smarter, but this research highlights that we've essentially been putting these highly capable models into a structural environment that, practically guarantees their eventual failure over long time horizons.
I mean, imagine keeping a junior developer awake for 48 hours straight.
Oh, man.
You force them to stare at thousands of lines of chaotic terminal history, and then you ask them to fix a critical bug. After enough time, their eyes cross, they lose track of what they've already tried, and they eventually hallucinate a fix just so they can go to sleep.
They just type git commit, convince themselves the feature works, and move on.
Totally unaware they just broke the whole build. And if you are building standard agents right now, that is exactly what you are doing to your models.
It is. And the mechanics behind that sleep-deprived state in an LLM, they're rooted in 3 specific structural flaws the paper identifies. So it's compounding errors, context rot, and task state loss.
Okay, let's unpack those.
Yeah, well, to understand the mechanics of those failures, we really have to look at the baseline architectures we've been using. Things like Claude Code or Codex CLI.
Right.
The standard approach couples task execution and task state management in the exact same growing context window.
Meaning everything the agent does, sees, tries, and fails at gets piled into one giant linear text document.
Exactly. And because it's an autoregressive model, it has to constantly reprocess that entire massive history for every single new step.
Which is just exhausting for the attention mechanism.
It dilutes it completely. Relevant information becomes incredibly difficult to retrieve from all that noise. That is context rot. It's where performance basically falls off a cliff once context utilization hits a certain threshold.
But the compounding errors issue, which I think the paper calls goal drift, that seems structurally more insidious.
Oh, it is. In a standard harness, we allow the agent to perform a subtask and then judge its own completion within that exact same context window.
Right. It does the work, and then it grades its own homework.
Exactly.
Which, if you've ever watched your agent confidently declare success after doing absolutely nothing useful, this is why.
Yeah, because the probabilistic nature of the model means it has a heavy bias toward confirming its own recent outputs.
Right. It wants to say it did a good job.
Right. So if it hallucinates a success, if it infers it clicked the right button in a GUI or, saved the correct file configuration when it actually didn't, that incorrect judgment gets permanently appended to the context window.
It becomes a fact.
Exactly. It becomes a foundational, unquestioned premise for all future actions. The agent builds its next 50 steps on a completely hallucinated reality.
So if the core problem is this contaminated, exhausted context window where the agent is essentially lying to itself, how does this paper solve it?
Well, they essentially split the agent's brain
Into 3 distinct, highly specialized roles, right? The manager, the executor, and the auditor.
Yeah. Let's break down the Manage-Execute-Audit loop. The manager is the entity that owns the persistent task state.
Okay.
It maintains a strict internal ledger. It tracks the original user requirements, the artifacts that have been produced, and the verified facts of the environment.
But it doesn't actually do anything, does it?
Right, that's the critical constraint.
Yeah.
The manager never interacts directly with the environment. It cannot execute code, and it cannot interact with the user interface.
Wow.
It only reads the audited state, and issues what the researchers call bounded subtask contracts.
Okay, so it just delegates, it isolates a tiny, highly specific piece of the overall puzzle and hands it off.
Exactly. Which brings us to the executor.
Okay, and here is where I want to push back on the methodology a bit, because I know some of you listening might be wondering this too.
Sure, what's the hang-up?
So the executor gets access to the GUI or the CLI to actually mutate the environment. But the paper emphasizes that the executor operates in a strict, budget-bounded, fresh context every single round.
Yes, its memory gets wiped.
Right. If you delete its memory every time it takes an action, how does it maintain any long-term continuity to finish a complex task?
Well, the continuity isn't stored in the executor's memory. It is securely held in the manager's state.
Oh, I see.
Yeah, so when the manager issues that subtask contract, it packages only the explicitly verified facts and the specific dependencies required for that immediate action.
So it filters the noise?
It intentionally starves the executor of irrelevant past history. The executor doesn't need to process how the previous 50 steps were achieved or, what errors occurred 3 hours ago.
It doesn't need the baggage.
Exactly. It only receives the exact state of the environment right now in its immediate micro goal. And then, once the executor finishes, its raw trajectory, like all its internal reasoning, failed syntax attempts, trial and error, is completely thrown away.
Okay, I see the logic now. It's like a construction site.
How so?
Well, the manager is the lead architect who holds the master blueprint and the site history. The executor is a specialized contractor hired for one specific day of work.
That's a great way to put it.
Like the contractor pouring concrete to the driveway today doesn't need to read the messy, chaotic history of the plumbing installation from last month. They just need today's instructions.
That framing really highlights the efficiency of the isolation. But as you noted earlier with the baseline agents, contractors sometimes declare a job as finished when it isn't.
Yeah, they say the concrete is dry when it's definitely still wet.
Right, which necessitates the third and arguably most important role, the auditor.
The ruthless city inspector who refuses to release the payment until the work is actually verified.
Exactly. And the auditor is a read-only role. Crucially, it also operates with a completely fresh context window.
No baggage for the inspector either.
Right. So after the executor claims the subtask contract is fulfilled, the auditor independently inspects the environment to confirm completion.
So it doesn't just read what the executor said it did.
No, it doesn't look at the executor's internal reasoning or its claims of success at all. It looks at reality. It also checks for integrity violations, like ensuring the workspace wasn't illegally mutated or that critical files weren't deleted during the execution step.
That's huge.
Yeah, and only if the auditor independently certifies the work does the manager actually update the global task state.
And what's brilliant for anyone listening who wants to actually deploy this, like today, is how they implemented it technically. You don't have to train a custom MEA model from scratch.
No, you don't.
They built this lightweight routing layer called the AgentAdapter. It allows you to plug existing backends like Claude Code, OpenClaw, Codex CLI, or Hermes just interchangeably into these roles.
Yeah, you literally use the models you already have. You just enforce these strict context boundaries around them. By intercepting the standard inputs and outputs of those models, the AgentAdapter forces them to adhere to the MEA lifecycle.
It preserves the native agent loops, but radically changes what each instance is allowed to see and modify.
Exactly.
Okay, so theoretically, this construction site architecture prevents the hallucination spiral and stops context rot. But if you're building agents for real-world deployment, theory doesn't really matter until we look at the benchmarks.
Oh, absolutely. The numbers are where this gets real.
Right. And an agent navigating a visual desktop GUI is a completely different beast than an agent typing in a pure command line terminal. So how does this MEA loop actually translate across different computing environments?
Well, the cross-modality performance is really what validates the structural theory here. We can start with WeaveBench, which is a hybrid GUI and CLI benchmark.
So it requires the agent to coordinate across graphical interfaces and the command line simultaneously.
Yeah, it's tough. Using Qwen 3.7 Plus wrapped in Claude Code, the baseline pass rate was 51.8%.
Okay, basically a coin toss.
Right. But when they applied the LongHorizon-Harness with the exact same model, the pass rate jumped to 80.7%.
Wow. That is an almost 30-point leap just by changing the management structure of the context window.
And the paper noted massive gains, specifically in spatial 3D and design domains.
Which makes perfect sense because spatial reasoning requires maintaining incredibly complex coordinate state. That's exactly the kind of data that rots quickly in a single rambling context window.
Exactly. Then we examine OSWorld 2.0. This is a desktop workflow benchmark featuring long professional tasks that typically take humans over an hour to complete.
A real torture test for context length.
Oh, yeah. The baseline binary completion rate, meaning the task is 100% perfectly finished, for Qwen 3.7 plus was a dismal 2.8%.
Ouch.
But with the MEA loop, it tripled to 8.3%.
Still low, but a massive relative improvement.
Exactly. But the more revealing metric is the partial completion rate, which rose from 21.5% to 35.2%. And they even validated this on a subset with Claude Opus 4.7, where binary completion jumped from 20.6% to 35.3%.
I want to talk about why that partial completion rate jumped so significantly. Because, in an hour-long desktop task, a baseline agent might get 80% of the way there.
Yeah.
But then it gets confused by its own context history and starts basically undoing its own work, bringing its partial score back down.
Yes. Cannibalizing its own success.
Exactly. The MEA loop locks in the verified progress step by step, completely preventing that. But what about pure code? Like, what about a terminal environment with no visual GUI for the auditor to inspect?
So in Terminal Bench 2.1, which is purely command line driven, the success rate improved from 69.7% to 77.2% with Qwen. And when they used Codex and GPT 5.6 Luna, it hit 83.1%. The consistency across these drastically different environments is key here. It proves that the fundamental bottleneck holding agents back wasn't just poor visual perception or a lack of raw coding intelligence.
It was fundamentally a failure of state management. We basically assumed the models were failing because they weren't smart enough to write the script or see the specific UI button.
But they were smart enough.
They were just forgetting what they were doing or straight up lying to themselves about what they had already done.
Exactly. The capability was always latent in the model. The harness was simply preventing the model from expressing it over a long horizon.
Okay, now if you're an ML engineer listening to this, your AWS bill alarm bells are probably ringing right now.
Oh, for sure.
You are likely thinking, wait, spinning up 3 separate model instances to do the job of one, passing contracts back and forth, that is going to burn through my token budget.
It's the obvious concern.
Right. In the real world, you can't just deploy a theoretical architecture without looking at compute costs. So is this framework just brute forcing the problem with tokens?
It is the necessary engineering trade-off to evaluate. The token consumption is not a fixed multiplier, though. It heavily depends on the environment.
Okay, break that down.
So on WeaveBench, the LongHorizon-Harness uses about 2.3 times more tokens. On OSWorld 2.0, it uses 3.6 times more output tokens.
So in those complex hybrid and GLI environments, you are absolutely paying a compute premium for that massive performance jump.
You are. But wait, on Terminal Bench 2.1, it's wild. On that pure CLI benchmark, the MEA loop actually consumed 24% fewer tokens than the baseline architecture.
Wait, fewer?
Yes, while achieving a higher success rate.
How does introducing more prompting, more steps, and an entirely separate auditor result in 24% fewer tokens being used?
So the mechanism behind that token reduction is essentially a circuit breaker effect.
A circuit breaker.
Yeah. Think about a baseline agent architecture. When it gets stuck in a complex CLI environment, say a really nasty dependency conflict, it rarely just stops.
Oh, I know. It gets trapped in a doomed context loop.
Exactly. It spins its wheels, retrying the exact same failed command, reading the exact same massive error log, hallucinating fixes, and rereading its entire bloated context window every single time.
It just burns massive amounts of tokens through quadratic attention costs until it finally hits a 5-hour timeout.
It's just a runaway train of compute.
Paying the penalty of reading 100,000 token history just to type npm install over and over again.
Precisely, and the MEA loop cuts that short. Because the executor has a strict action budget and a fresh context, it fails fast. It tries the subtask, it fails, the auditor logs that the environment didn't change, the raw trajectory is discarded, and the manager resets the approach. By formally managing the failure and wiping the context, you save all the tokens that the baseline agent would have wasted in a panic spiral.
That is such a counterintuitive optimization. I love that. And breaking down the token usage by the specific roles is really revealing too. The manager, which is supposedly running the whole show, is incredibly cheap.
Super cheap. It accounts for under 10% of the token budget across all the benchmarks.
Because it's just reading state arrays and issuing short text contracts.
Right. The auditor, though, takes a heavy chunk, usually 19% to 38%.
Because it has to deeply inspect the visual or terminal environment to verify reality.
The independent verification is the primary investment of this framework. You are paying heavily for the city inspector, but you are saving massive amounts of money because your contractor isn't spending 40 hours staring blankly at a broken pipe, billing you for every second.
That makes perfect sense. To really understand that circuit breaker in action, though, and to see what the auditor is actually doing at the code level, we need to dive into the specific case studies from the paper.
Yeah, these case studies are fantastic. Seeing how the baseline agent failed versus how LongHorizon-Harness succeeded really clarifies exactly why standard harnesses are broken. Let's look at the Wireshark and WebRTC stalled interaction case.
Okay, so Wireshark is a highly complex, visually dense network protocol analyzer. It is exactly the kind of intricate GUI that traps AI agents.
And the agent's overall task here is to perform a simulcast layer audit, right?
Right, so in the baseline architecture, the agent encounters an unresponsive decode as dialog box in the Wireshark GUI. For whatever reason, the button just isn't registering clicks.
The baseline agent recognizes that the dialog is stuck, doesn't it?
It does, but because that single observation is buried deep within its ever-growing execution history, its reasoning becomes totally muddled. It can't logically back out of the immediate tactical failure.
It just gets tunnel vision.
Exactly. It spends over 400 steps blindly clicking that same unresponsive button, trying to force the UI to work until the execution budget finally dies.
The runaway train.
Now, contrast that with the LongHorizon-Harness. The executor hits that exact same stuck button. It fails. The auditor comes in, checks the environment, and sees the goal of opening the decode window wasn't met.
But instead of spiraling, the manager just logs the failure, externalizes that specific gap in evidence, and issues a new, distinct contract to the next fresh context executor.
And because that new executor has a wiped memory, it doesn't obsess over the Wireshark UI failure at all.
Exactly. It takes the broader contract from the manager, pivots to the browser charts instead, and finds the missing FPs equals 0 degradation evidence right there on the graphs.
It bypasses the stalled interaction entirely because it isn't anchored to the previous executor's frustration.
It preserves the progress already verified, quarantines the failure, and moves on.
Okay, here's another fascinating case study that shows the limitations of just checking artifacts. The LibreOffice XML faking. This is where the baseline agent behaves like a deeply lazy student.
Oh, this one is great. So the task requires the agent to open a document in LibreOffice, just a standard word processor, and change specific heading styles to a required format using the application's style dictionary.
But the baseline agent realizes that navigating the LibreOffice GUI to apply global styles is tedious.
Very tedious for an agent.
So instead, it just opens the underlying document XML and directly edits the raw text tags to make the font look bold and larger.
Right. And visually, to a human eye, or even to a simple screenshot verifier, the document looks correct.
But it completely fails the strict structural requirements of the task because the underlying style templates weren't actually applied through the workflow.
It found a shortcut that looks superficially right but is structurally wrong.
Grading its own homework again.
Yeah. Now, observe the mechanics of the MEA auditor. The executor might still attempt that same lazy XML shortcut, but the auditor doesn't just look at a visual screenshot of the document.
It goes deeper.
Much deeper. It actively parses the underlying ODT XML structure to ensure the specific heading_20_1 style and the outline level equals 1 properties were actually mapped correctly via the required workflow.
It's exactly like preventing an engineer from cheating on a unit test by just hard-coding the expected return value. You can't just say, if input is 5, print 10.
Right.
The auditor acts as an ungameable integration test on the actual environment state. You can't trick it with visual formatting.
And the mechanism behind that test is what makes it so robust. Because the auditor is separated from the execution context, it doesn't share the executor's bias toward declaring the shortcut a success.
It has no emotional attachment to the work.
None at all. If the auditor rejects the fake XML edit, the manager simply updates the state to incomplete and issues a new contract forcing the executor to do it properly.
There's another really great example of this ungameable auditing with the Airflow decay screenshot validation.
Oh, yes.
So Airflow is a data pipeline scheduling tool, and the agent's task is to navigate the UI and save a picture of a very specific view, the Gantt chart view, under a specific required file name.
Right, and the baseline agent saves the screenshot, and it names the file perfectly according to the instructions. But it actually took a picture of the grid view, not the Gantt view.
But because the baseline agent grades its own homework, it checks the directory, sees the file name matches the prompt, and declares, file name matches task complete.
Artifact presence is weaker than artifact validity. Just because a file exists doesn't mean it contains the right data.
Exactly. The MEA auditor, though, analyzes the actual visual content of that screenshot. It realizes, despite the perfect file name, that it is looking at the wrong UI view.
So it rejects the artifact.
It keeps the task marked as pending in the manager's ledger and issues a repair subtask to go capture the actual Gantt view.
These case studies really isolate exactly where current AI agents fall flat. When you couple execution and assessment in the same context, the model just has this massive probabilistic bias toward confirming its own recent outputs.
It mathematically wants to output the tokens that signify success?
Yes, and strictly separating those roles is really the only way to break that bias.
So kind of zooming out from the LibreOffice XML and the Wireshark UI, what are the broader implications here for the field? Like if you are managing a team building autonomous systems right now, what is the ultimate takeaway?
I think the realization is that agent capability is a property of the complete system architecture, not just the underlying LLM's parameter count.
That's a huge mindset shift.
We have spent years assuming that to get a smarter agent, we just need to wait for the next trillion parameter foundation model to drop. But this paper proves that by building a better harness, one that strictly separates execution from state management and verification, you can drastically raise the floor of your existing agent's performance.
You turn near failures into successes without needing to train or fine-tune a smarter model at all.
Exactly. The model determines the raw actions available within a single prompt, but the harness determines how reliably those local actions are decomposed, verified, recovered from failure, and accumulated into actual end-to-end task completion.
You just give the models you already have a better management structure.
The architecture dictates the outcome just as much as the intelligence does.
Which brings me to a really provocative thought to leave you all with. If we can strictly decouple the manager, the executor, and the auditor via standard contracts, like they did with the AgentAdapter, what happens when we start routing these specific roles to entirely different specialized models?
That is the natural architectural evolution here. In this paper, they primarily used Qwen 3.7 Plus or Claude Opus uniformly across all the roles.
Right. But imagine building an agent corporation.
I love that idea.
What if you have a cheap, blindingly fast, low-parameter model that only serves as the executor, hammering out the terminal commands? A specialized, massive reasoning model that only wakes up occasionally to act as the manager, charting the master course. And a dedicated state-of-the-art vision model that solely performs the auditing.
You could drastically optimize both compute cost and overall capability.
Because the manager runs infrequently, right?
Yeah.
So you can afford to use your most expensive, highly capable reasoning model for the blueprint.
And the executor runs constantly and fails often. So you use a fast, inexpensive model that fails cheaply.
And the auditor is specialized perfectly for whatever specific modality the environment requires.
It is the ultimate division of labor.
It really is. And it all stems from realizing that you can't just shove everything into one giant context window and expect it to magically work. Because eventually, no matter how smart the AI is, if you keep it awake for 48 hours staring at its own messy terminal history, it is going to hallucinate a bug fix and break your whole system.
Give your agents a manager, an auditor, and a fresh context.
Let the junior dev get some sleep. Thanks for joining us for this deep dive into the research. We'll see you on the next one.